Hi, Raymond. Thanks for your question. So this is about task scheduling, and the order in which tasks are scheduled the same as when they will be given to an available thread. So the order in which tasks will be executed may be different from the order in which they were generated. Yes, so it's entirely up to the implementation to do what it likes. Every implementation is different, but a fairly typical strategy is for every thread to have its own queue of tasks. So when a thread generates a task, it will typically put that on its own queue, and it will preferentially execute tasks from its own queue until it runs out, in which case it will steal tasks from other threads' queues. And then you have a choice of whether you do last in, first out queues or first in, first out queues. And there are some advantages to both. Last in, first out has some potential benefits because you are likely to get better cache behavior, because any data associated with the task has been recently accessed, and so is more likely to still be in the cache. But it's entirely an implementation choice as to what happens. No, it's is it similar to that? It's kind of solving a slightly different problem, and it's much more. It has to be much more dynamic, because with something like a batch scheduler, then the jobs come with the jobs come with an estimate of how long they're going to take. Okay, when you submit a batch job, you tell it how long you want it to you reserve a particular time slot and resources. For task scheduling, basically the runtime has no such information about task durations. So it has to be kind of more flexible and dynamic system. So it can't sort of plan ahead and reserve slots for tasks effectively, because it has no idea how long they're going to execute for. Okay, so welcome back, everybody. So let's make a start on today's session. So first up today is a set of tips and tricks and things to watch out for. So these are kind of practical hints for working with OpenMP that you might, that sort of don't naturally fall into a place where we sort of talk about the actual syntax of directives and so on. So and these are not really in any particular order. So it's a collection of things that I've put together from having taught OpenMP for a long time and observed people using OpenMP and answering people's questions and fixing people's problems. Okay, so first up, yes, directives. Be careful if you make a typo in the OpenMP directive Sentinel, then at least for some compilers that will not raise any error message. So that's potentially dangerous, particularly if it's a synchronization directive like atomic or critical. You can just end up with a race condition and you with no warning. So that's rather unpleasant. If it's OMP parallel or OMP parallel 4, then you just get no parallelism and you wonder why. But that's kind of less, maybe slightly less dangerous. Okay. So the way OpenMP directives are designed, so that in C, C++, they're preprocessor pragmas, and in Fortran they are comments. That's a deliberate choice to help you be able to write code that works both as a OpenMP parallel code and as a plain old sequential C, C++ Fortran code. So it's quite a convenient feature to allow you to build both parallel and sequential versions from the same code base without having separate versions. So that's the idea. Of course, it doesn't quite work because of things like if you've got if you're calling runtime library routines, then those, unless you compile with OpenMP enabled, those won't those won't get linked in, and you get linker errors. So you need something a little bit more, and for conditional, one solution is to do conditional compilation, and the convenient way to do that is to use there's a macro _OpenMP, which is that's part of the specification. That will be defined if the code was compiled with the OpenMP switch on. So you can use ifdef _OpenMP as a portable preprocessor switch to conditionally compile code that contains OpenMP runtime library stuff or anything else that's related to OpenMP parallelism, or else compile the regular sequential equivalent code if not. So that's quite handy. So it gives you and that's guaranteed to be portable across different implementations. Okay. So next up is straying a little bit into the performance issues, which we're going to cover in much more detail in the second topic today. But just to have a rough idea, the overhead of executing a parallel region is typically in the sort of few microseconds to a few tens of microseconds range for most implementations. Obviously, it depends on the implementation, which compiler you're using, depends on what hardware you're running on, it depends on how many threads you're running. So there's some, there's a range of values, but it's in that sort of order of magnitude. So that's quite small, but it's not nothing. Okay, so you can actually do if you have fairly highly optimized code, you can do quite a lot of floating point operations, for example, in 10 microseconds. So it's just to be worth aware that the sort of granularity of code blocks or loops that you need in order to make it worthwhile parallelizing, and so that any parallel benefits you're gaining are not just washed out by the overhead of starting and stopping parallel regions. So really, the sequential execution time of a section code has to be, at least that, and preferably, you know, an order of magnitude bigger than that to make it worthwhile. In some applications, you might find you're in a situation where you have a loop which you're going to execute lots and lots of times, and maybe the iteration count varies a lot from one instance to another. So you might be in a situation where sometimes the loop execution time is really short and it's not worth parallelizing. Other times it's really long and it is. So you can use the parallel region comes with an if clause to decide whether to go parallel or not. Okay. And if the if clause evaluates to false, then technically you still get a parallel region, but only with one thread. And so, but the overhead for a parallel region with a single thread is not 0, but it's typically much smaller. It's typically a lot less than a microsecond. So that's a fairly convenient way of dealing with that situation where you have a parallel region which is only sometimes computationally expensive enough to be worth parallelizing, and other times it isn't. Okay. So a question that comes up sometimes is, you know, how reliable is what can I rely on in terms of if I use a schedule clause on a work sharing loop, what guarantees do I have about the mapping of iterations to threads? So I've had an example like this where I have 2 loops inside a parallel region, and the first one writes some values into an array A, and the second one reads values from the same array. Then the question is, do I actually need the barrier synchronization between these 2 loops? Is it safe to use a no wait clause on the first loop to get rid of the implicit barrier at the end of the first parallel loop? And the answer is, well, this is safe under certain circumstances, because if the number of iterations in the 2 loops is the same, and the schedules are the same, and the schedules are static or static with a chunk size, then you are guaranteed to get exactly the same mapping of iterations to threads for both loops. So that means that the no wait is safe, because we're now absolutely guaranteed that the thread that writes AI, a particular AI, is going to be the same thread that reads AI in the second loop. And so the barrier synchronization isn't necessary. So there's a kind of interesting, there's a slightly more interesting use case for this, which is, suppose I have a loop nest where the outer loop has some dependency. Okay, so in this case, I've got a J loop enclosing an I loop. So the I loop is parallel. But the J loop is not, because of this dependency on J minus 1. Okay, so the J loop iterations have a dependency, which means they must be executed in sequence. So I could potentially just put OMP parallel 4 around the inner loop here, around the I loop. But what's likely to happen is that the I loop doesn't really contain a single instance of the I loop doesn't really contain enough work to be worth parallelizing. The overhead of the parallel region will be too much. So there's this kind of slight trick or interesting pattern that you can use, which would be to put the parallel region round the outer loop and use a for directive with a no wait clause on the inner one. Because again, because of this property, because we've got a static schedule, we're guaranteed that every instance of the I loop is going to have its iterations mapped to threads in exactly the same way. Means that because there aren't any cross thread dependencies going on here, so it is safe to use no wait. That gets rid of the barrier. And actually, the most of the cost of the parallel region is, in fact, the barrier synchronization at the end. So there's still a bit of overhead, but not very much for the work sharing for. But this pattern tends to be an efficient way of dealing with this kind of pattern. So in general, in some cases, you might be able to interchange the loop order, but in a case like this, you wouldn't want to do that because of the memory locality issue. So you really want the I loop innermost, because that's indexing the contiguous elements of the array A. So that's better. That's the right thing to do for sequential performance in terms of cache behavior. So that this is quite it's a bit of a trick, okay? But it's a way of parallelizing an inner loop without incurring excessive overheads from synchronization. Okay, so sticking with loops. Okay. So it turns out that if we have loops with load imbalance and we need to choose a suitable schedule, so to try and get the load balance right, so maybe static with a chunk size or dynamic or guided schedule. But for static and dynamic, we have to choose the chunk size, and tuning the code can be quite difficult because the optimal chunk size may depend fairly strongly on the number of threads that are used to execute it. And in general, we want to write code that will work on any, will work well on any number of threads and not be specialized for a certain number of threads. So it turns out that it's actually more, rather than tuning the chunk size directly, it's often more robust to tune the number of chunks per thread. Okay, and derive the chunk size from that, and that's possible because in the schedule clause, the chunk size expression does not have to be a compile time constant. It can be a runtime evaluated expression. So you can do something like this. You could have a variable called so C per T is supposed to stand for chunks per thread here. So you have a variable whose value you can tune, and then you use that to derive the chunk size. So that's probably a more robust parameter to tune. It's that's more likely, if you find a good value of number of chunks per thread, then that's likely to be a good value for a wide range of thread numbers. Okay. When we're executing inside a parallel region and we have a block of code that's executed by only one thread, then we have choices. So we can either use single or master. So just to remind you, so single means the block of code will be executed by the first thread that gets there, and the other threads will skip over it. Master means that it's thread 0 that will execute it. So which one should you use? Well, you have some choice. Depends how on the situation. Master typically has lower overhead because it's just implementation of master is trivial. It's just a test on the thread ID. But single requires some internal synchronization because you might have the situation where two threads both arrive at the single at the same time, and they have to synchronize correctly and agree that one thread's going to execute the block and the other one isn't. But you just have to remember this strange asymmetry between these two. Okay, so single has an implied barrier at the end of it, which you can get rid of with a no wait clause, whereas master does not have an implied barrier, though you can add an explicit barrier directive after the master if you want. So you can have, you can have either behavior, so a barrier or no barrier in both cases, but the default behavior is different. It was just a bit of a weird decision. I think that was made at the very beginning of OpenMP, and with hindsight, it probably doesn't really make a lot of sense that it's like this. But it's one of those decisions that was made once, and you can't undo it easily. On the other hand, if you have some reason to expect some threads to arrive at this block of code before others, then it's worth using single, because the first one thread that gets there can go ahead and start executing it. Doesn't have to wait for the master thread to arrive, which might be later. Okay. So moving on to a bit about data sharing attributes. Pretty common bug. Don't forget that private variables are uninitialized on entry to parallel regions. So variables that appear in a private clause on a parallel region or a task or other constructs. So you can have private clauses on work sharing constructs. It's not a very common use case. But if you do that, don't forget that those things are uninitialized on entry. So every thread gets a new copy of that storage, but it has no valid value. So of course, you can use first private to give private variables an initial value, but it's more likely just to be a mistake, okay? Because it actually turns out that at least for parallel regions, okay, tasks are different, as we saw the other day, but for parallel regions and parallel loops, the use cases for first private are actually surprisingly rare. So it's always worth just, if you think you need first private on a parallel region or a parallel loop, then it's worth just checking in and thinking twice about it. And you say, am I sure that's really what I need? Or am I just making pointless copies of things? Okay. So this is about the default behavior for data scoping. So for parallel regions, the default behavior is the same as default shared. Okay, so if you don't put a default clause on, then most variables which are in scope outside the parallel region and are used inside it will be shared by default. Okay, and this is possibly, at least in my opinion, this is the worst design decision that was made in OpenMP. Okay, it's actually really dangerous. It makes it far too easy to accidentally share variables and have race conditions. So my advice is always use default none. Okay. So why? you might think, well, is that not a bit overkill? And I've forced myself to type everything into a shared or private or first private or a reduction clause or whatever. Is that not just a bunch of, that's a bunch of extra typing and mess in my code that I don't need? Well, what I've noticed from observing people programming is that there's this effect which I call variable blindness. Okay, and what I mean by that is that if you give somebody a block of code and ask them to list all the variables that are accessed in it, they will typically miss some. Okay, they will just look at statements where variables are being assigned and not at other things. Okay, so they will people will miss things which are things like variables that appear inside loop constructs, so inside do or for things, so things like loop bounds. They will miss things that are inside, that are inside if tests. They will miss things which only appear as maybe only appear as indexes into arrays or arguments to called functions. So it's if you think it's easy just to to make to eyeball a piece of code and make sure that you've thought about all the variables, it's actually surprisingly difficult to do that reliably. So I strongly recommend using default none and listing everything explicitly. Compilers are pretty good at generating error messages. So if you miss something, if there's a variable that doesn't appear in one of the clauses, then you will typically get a sensible error message that says, variable X did not appear in a data sharing attribute clause for on the parallel region at line 273. So it's you can use default none to make sure that you have as a pretty reliable way of making sure you haven't missed anything, and there isn't something there that you haven't that is going to get accidentally shared, or so something that maybe should be a private variable or should be a reduction, and you end up with a race. Okay, so and the problem is that it's race conditions are nasty. They are there's no good way of testing for them without using specialized tools, which I'll cover later. I'll come back to later. Okay, so I have a code like this, which has a bug, right? So there's no default clause, there's nothing declared here, everything's shared by default. So in particular, this variable temp will be shared variable, which is incorrect. It needs to be private. The nasty thing about something like this is that if you compile this code with sufficient compiler optimization turned on, so with an optimization, with probably even 01 will probably do the job, then the compiler will never actually store the value of temp in memory anywhere. It'll just use a register for it. So what's effectively happening is that the compiler optimization is doing the privatization for you. And that's fine, but what it means is that you will always get the right result. You'll never see a race condition happen until you or somebody else builds the code without optimization. And then that'll expose the race condition. Or you might, change compiler, which does the optimization differently, or fails to do the optimization for certain cases, and you suddenly expose a race condition. So it's things like that. So this is why it's worth being. Race conditions are very nasty bugs. So it's worth being as defensive as possible to try and avoid having them introducing into the code in the first place. Much better that you never write race conditions rather than that you write them and then try and fix them afterwards. Okay. So Joey says, aren't variables declared inside parallel regions private by default? Yes, they are. Yeah, so that's no problem. Okay, so if you declare it, if everything that's private is declared inside parallel regions, that's fine. Not a problem. No, temp's not declared. If I said int, if I put int, I would need int temp in there. Okay. So if I had int temp, then that would be private. But but as it stands, it isn't. Okay, and this is a nasty little feature to do with global variables and private clauses. Suppose I have a global variable, it's maybe declared at file scope called foo here, and I have a parallel region where foo appears in a private clause. So I get private copies. I want private copies inside the parallel region. The parallel region calls a function called sumfunc. So, and sumfunc also accesses the same global variable foo inside. Okay. So question is this okay? And the answer is unfortunately no. Okay. Because it's then unspecified as to what this actually refers to. Okay, so this reference to foo might be to the original global storage, or it might be to the private copies. You don't know. Okay, it'll be one or the other, but you don't know which it's going to be. So in general, this pattern is unportable and therefore not usable. So you can't reliably do this. The problem arises because the compiler might decide that it wants to inline the body of some func into the parallel region, and for some technical reasons it's very difficult for the compiler to do that and correctly resolve the right references. Okay. So if you want to do this, if you really want to access the private copy, then you need to pass it through the argument list. Or if you want private copies, if you really want private copies of global variables, then you can use thread private. Not a nice feature, but sometimes that's just the simplest thing to do. Oh, yes, you're right. That's a typo. Thank you. Okay, so this one is basically for Fortran if you're for Fortran programmers. So unfortunately, this kind of thing is getting rarer as old codes die, but you still might be unlucky to be handed an old-fashioned Fortran code and be faced with this kind of problem. So you have a loop which has and the loop body is several pages of code, hundreds of lines of code referencing hundreds of variables directly inside the loop. So if you want to parallelize that loop, you are then faced with the problem of trying to determine the correct scope for all those variables, which is kind of tedious and error prone and difficult to test properly. So if you're faced with that problem, what I would suggest you do is you actually refactor the sequential code so that you put the extract the loop body into a subroutine, and then everything that's anything that you can make local to the anything that you can declare locally inside, that's basically loop temporaries. You declare them inside the declaration of the subroutine and pass everything else through the argument list. So that refactoring is, you're essentially making more or less the same decisions as to whether things need to be private or shared, but you're doing it in an environment where it's just a sequential refactoring, and you can test for correctness much more easily. So again, obviously, this doesn't really happen typically for in C or C++. You can just declare the temporaries in the scope of the loop body anyway, and that would also be the sort of natural coding style to use, which isn't available to you in Fortran. Okay, so another nasty place where you can accidentally get a race condition where you might not expect it is if you have reductions on work sharing constructs. Okay, so sometimes you might want, in a case like this, where I have a loop which needs a reduction for sum here, and I have to put the reduction on the work sharing directive because I want the reduced value of sum sometime later in the parallel region. Okay, so I can't put the reduction on the parallel directive, because then the reduction wouldn't happen until the end of the parallel region. So I do this, then well, technically this is a race condition anyway, okay, because this initialization of sum is inside the parallel region. So I've actually got so this is one of these harmless looking races, but as far as OpenMP is concerned, so OpenMP specification is very clear about race conditions. It says that you're not allowed to do them, okay? No matter how harmless they are, then if you code race conditions, then the results of what you get are there's no guarantee as to what happens. So you might think, well, it's perfectly, this is one of those harmless ones, okay? What is it not okay for just every thread to set sum equal to 0 before doing this loop? And the answer is no, because there is no synchronization at entry to the work sharing for loop. Okay, so as soon as a thread has set sum equal to 0, it goes straight ahead into the loop, and what could happen is that one thread finishes all its loop iterations, it adds its partial sum value into sum, and then at some point later another thread comes along and resets the original storage to 0 again. So there is actually a harmful race condition here, which is between this initialization and the actual write. There's an implicit write here. Yeah, so there should be you're absolutely right, Gervais. There needs to be a barrier between the initialization and the start of the loop. And to be completely correct, you also need to make sure that this is really only executed by one thread. So if you're going to be properly correct and avoid any race conditions, then you should put the initialization of sum into a single, for example. Okay, so single has a barrier, or you could do it with master and an explicit barrier would also work. So in this example, obviously, you could just move the initialization of sum outside the parallel region, but that's not always possible. If there is, example, if there's a sequential loop inside here around all this, then you have to be able to reset sum for every loop iteration. So you would still face the same problem. Okay, so this is an interesting one. So sometimes what can happen is if you take your sequential code, you do nothing to it, you don't add any OpenMP at all you do is you change your build procedure to add the OpenMP flag to the compiler. And suddenly your code breaks. Okay? So it works fine if you compile it without OpenMP, and it's still a sequential code. You compile it with the OpenMP flag, and it dies somehow. What can happen? Well, compiling with the OpenMP flag does something, okay, even to sequential code. And what it does, one of the things that it does do is that it forces all local variables to be stack allocated and not heap allocated. So in general, if for plain old sequential code, the compiler has a choice, okay, for local variables, particularly sort of local arrays inside functions. The compiler can choose as to whether it puts them on the stack, or if it knows they're quite large, it may just decide to heap allocate them instead. So compiling with the OpenMP flag forces everything to go on the stack. So a couple of things can happen. It might just cause you stack overflow, okay, and you get the usual nasty death modes from Stack Overflow, which is either corrupted data or seg faults. Or it might also expose a bug in your code, which is, if you assume that some contents of a local variable are preserved, if you are making some assumption that the contents of local variables are being preserved between function calls without using static or save in Fortran correctly. So you can use static or save, but then to force, that forces heap allocation and persistence. But by OpenMP's rules, those variables are then shared by default, which may or may not be what you want. Okay, so you might need to actually make them thread private to give every thread a private copy, for example. And one pattern, for example, that typically makes use of this is like first time through code. Okay, so you have a static flag which is initialized to 0 whenever, and you test that, and the first time that function is executed, you execute some block of code, and then you set the flag to 1 or whatever, and then that block, and then subsequent executions never re-execute that block of code. So things like that you might need to think quite carefully about, particularly if the first time through is going to happen inside a parallel region. Then what does that even mean? Okay, so does that actually make any sense? Do you want all the threads to execute it, or do you want one thread to execute it and not the others, or what? Okay, so you might need to think rather carefully about what happens to that sort of pattern. Okay, so if you're running out of stack size, and that's possible just if you have large private data structures, it's so it's possible. It's easily possible to run out of stack space. Okay. So you can increase the amount of stack space available, but the way you have to do it is slightly messy. So the size of the thread stacks, apart from the master thread, you can control with an environment variable called OMP stack size. But that doesn't affect the size of the master thread stack. That has to be controlled in the same way as you would for a sequential program. So that might be a compiler switch, or on Linux systems, you can use a ulimit command, for example, to increase the stack size for processes. So this is slightly messy, and the reason why it's like this is that OpenMP isn't able to control the master thread stack size, because that's controlled by the operating system when it creates the original process. And by the time the OpenMP library can possibly get invoked, even if that's at program startup, it's then too late to change the stack size. Okay, next one. Just remember that you can't use critical and atomic to protect the same memory location. So a pattern like this, a parallel region, have an update to A, which is inside a critical region, and another one that's inside an atomic region. That's not safe. Okay, so one thread could be executing the critical, another thread could be executing the atomic at the same time. Okay. Next one is allocating storage based on the number of threads. Okay, so sometimes you might want to allocate some storage whose size is determined by the number of threads. Okay, so you might want an array that's where one of the dimensions is the number of threads. Okay, but how do you know how many threads the next parallel region is going to execute? Okay. So, we talked a bit about internal control variables the other day. Okay, so this is basically the way of getting hold of that. So the nthreadsvar internal control variable, well, at least you are guaranteed that the number of threads used for the next parallel region which this thread encounters will not exceed this value. Okay. And you can retrieve the value of this internal control variable by calling OMP get max threads. Okay, so just remember that this is, there is this unfortunate naming convention. So OMP set num threads sets the value of this thing, but OMP get num threads does not return its value. Okay. So that works unless you use a num threads clause on the parallel region, because that will override the internal control variable. Okay, it's always worth noting, and if we want to have robust programs, then it's you have to always consider it's always possible that the implementation might decide to deliver fewer threads than what you asked for. Okay. So if you are, as I say, in general, it's best not to. But if your code does depend on there actually being a certain number of threads, and there are some, it's possible to code patterns which don't work on a single thread. So if your code actually depends on there being a certain number of threads present in a parallel region, then you should really always call OMP get num threads inside the parallel region to check that you actually got the number of threads that you were expecting. So there is, if you look at the OpenMP specification, there's actually quite a complicated algorithm for determining exactly how many threads you get, but the implementation always has a get out, which says that it's always allowed, for whatever reason it feels like it, to give you fewer threads than what you asked for. Okay. So some of the OpenMP environment variables are ones which can affect performance, and you might want to consider setting those, or at least checking that the defaults are the right ones, because the default values are typically implementation dependent. So there's a few of these. First one is OMP wait policy. So setting that to active will encourage your idle threads. So threads which are doing nothing. So maybe threads between parallel regions, or threads waiting at a barrier, or threads waiting to acquire a lock, enter a critical section. So wherever threads are idle, so this encourages them to spin rather than to go to sleep. What most implementations will actually do with idle threads is it'll typically make them actively spin for a while, and then eventually they'll get put to sleep. But what this does is, so this is really just a hint, but it kind of encourages the implementation to keep them spinning, or to basically increase the interval from which they're going to spin before they get put to sleep. So if threads are spinning, then they're actively consuming CPU cycles, but it makes them really quick to reactivate them. If they go to sleep, then they're not consuming CPU cycles, but there's then some cost for waking them up again. Okay, next one is OMP dynamic. Okay. So again, poor naming choice. This is nothing to do with dynamic loop scheduling. Says, well, again, this is really just a hint. Okay. So as I said just now, it's always possible for the runtime to deliver fewer threads than what you asked for. But this is a kind of a hint, saying really, please don't do this unless you absolutely have to. If you do something, make some horrible error somewhere, and you ask for 1 million threads, then you probably want the runtime to refuse to do that. Okay, but otherwise, setting OMP dynamic equals false will try to discourage the runtime from delivering you fewer threads than what you asked for. If you set it to true, then what implementations will do is will probably monitor the system load, and will basically decide the number of threads to give you based on how many on the available free hardware resources that are in the system at the time, which that may be what you want if you're working on a shared system, but for in most cases, if you're working on HPC systems, you really don't want that. And the last one is OMP proc bind equals true. Okay, so this prevents threads from migrating between cores. So again, if you're running under a batch system, then typically the batch system will take care of that for you, or at least some nasty collaboration between the batch system and the OpenMP runtime is going on to make sure that that your threads get bound to cores. And so it's somewhat tricky to get that set up correctly. So depending on what system you're running on, that may not have been configured correctly. So it's worth thinking about. But a system like ARCHER2, the combination of Slurm and the OpenMP runtimes do make sure that you get that OpenMP threads get bound to different hardware cores. But things can go wrong easily. You can get threads not bound to cores, or you can get threads bound to hardware threads instead of separate physical cores, and yeah, things can go. There are lots of ways that can potentially go wrong. Okay, so just one or two other things about tools. Okay, so for terms of debugging and so on, so traditional debuggers, things like DDT, TotalView, etc. which are the sort of things you're likely to find on HPC systems, do have support for OpenMP, which is great, but traditional debugging is not much help for tracking down race conditions, particularly because running under the debugger will change the timing of events on different threads. So it's very possible for you've got a race condition, you get wrong and non-determining answers from your program. You run it under a debugger, and the race condition goes away because it's forcing some ordering of execution between the threads. However, there are some tools that will try to do race detection, and they work in a very different way. They don't do traditional debugging, stepping through code or like normal debuggers. What they do is instrument the code, and then they will capture all the memory accesses that happen during a run, and then analyze that data, that trace data, for races which might have occurred. So they record all the memory accesses, all the synchronization points, and then they post-analyze that trace to see whether there were any potential accesses that were incorrectly synchronized. So there's an Intel tool, Intel Inspector. It's one that's part of the Valgrind suite, and there's also Clang Thread Sanitizer that do this sort of thing. Using them is, as with all tools, there's a bit of a learning curve. You typically want, in order to generate gigantic traces, you would normally want to run with a small problem size, but fortunately, in almost all cases, the choice of problem size and inputs probably doesn't make the race condition present or not present. And obviously, you've got code path choices; they might do, but just problem sizes probably doesn't. So you probably want to run with a suitably small problem size so you don't generate gigantic traces. And some of these tools are also prone to false positives as well. They can do things like they will detect race conditions inside libraries somewhere, which they might technically be race conditions, but they're probably okay. It's probably not something to worry about. But you can end up with a lot of those, and sifting through them is a problem. Okay, and last but not least, timers. Okay, so if you're going to use a timer to measure the performance of OpenMP code, make sure that your timer does actually measure wall clock time. Okay. So, encourage you. OMP get W time is a good one. Okay. So might as well use it. But other things, so for example, the sort of Linux clock routine is not a wall clock timer, and you will see this used in some applications. And what that does in a multi-threaded context is what you're measuring is the CPU time accumulated across all threads in the process. So that's really not what you want, or at least it's probably it's not what you're expecting. Okay, so why don't I see any I'm timing my code and it's I don't see any speed up at all. Well, yeah, okay, your accumulated CPU time is not going to go down. Okay, no matter how well you parallelized your code. So that's one to watch out for. So particularly if you inherit code from somewhere that already has timers implemented on them, do have a check and see what it is it's using. Okay. Anybody have any other questions about that? If not, let's give ourselves a 5-minute break and resume at 10 past. Great. So second topic for today is performance issues. So with OpenMP, writing correct OpenMP code is generally speaking only half the game. So it's very easy to get into the situation where you've got a correct functioning OpenMP program, but the performance wasn't really great. Okay. So what's causing the loss of performance? Why don't I get perfect speed up? And the way I like to think of it is that it's gone into some sort of overhead. Okay. So, and I think it's helpful. I find it helpful to think about what are the different types of overhead can we get that will cause loss of performance for OpenMP programs. So there's six and a half, okay, so different categories which we'll go through in more detail. So those are sequential code, idle threads, synchronization, scheduling, communication, and hardware resource contention. And the half is compiler non-optimization, which we'll look at the end. So let's have a look at each of these possible problems, what causes them, and possible ways to avoid them. Okay, so sequential code. So I mean, this is kind of obvious one. You know, in OpenMP, anything that's outside of parallel regions or inside master and single directives is being executed sequentially, and the time spent in that code that will limit Amdahl's limit performance. That's just simple statement of Amdahl's law. Okay, so for example, if 20% of the original execution time is not parallelized, you're never going to get more than 5 times speed up, no matter how hard you try. So if that's the case, then and we can know that by profiling or timing measurements, then basically we haven't really finished the job. Okay, there's a significant time being spent executing sequential code. Then we need to do more work to find ways of parallelizing it. Okay, so nothing conceptually difficult there. Of course, solving the problem might be difficult, but conceptually, it's obvious what's going on. Okay, next one is idle threads. Okay, so this is typically caused by some threads finishing some piece of computation before others, and have to wait for other threads to catch up. Okay, so for example, threads sitting idle in a barrier at the end of a parallel loop or a parallel region. So OpenMP has a lot of implicit barriers typically, so there's a lot of places where threads are waiting for each other. Yeah, so this is just supposed to be a simple sort of activity diagram. So I've got 4 threads executing some parallel region or some parallel loop, and the blue stuff is the useful computation. And so, if there's a barrier at the end, then clearly, all threads have to wait for the slowest one to catch up. So the other threads will be idle for a certain amount of time, which is causing some overhead. Okay, so this is just straightforward load imbalance in this case. Okay, so what can you do about load imbalance? Well, if it's a parallel loop, we can obviously experiment with the different schedule kinds and chunk sizes, and you can use the schedule runtime option to avoid recompilation. So it allows you to set the schedule with an environment variable. So we talked about the other day for irregular computations using tasks can be helpful. The runtime is going to take care of the load balancing for you. Just as a word of warning, it's not necessarily always safe to assume that 2 threads doing the same number of computations will actually take the same time to execute them. Okay, just because they're doing, they're executing effectively the same code and doing the same number of, say, floating point operations, does not necessarily imply they're going to take the same amount of time. And why not? Is because the time that's taken to load or store the data may be different depending on if and where that data is cached. And so if all the data is in the cache where one thread is executing, then that thread will execute that block of code faster than other threads. Okay. You can also have idle threads where we have lock type synchronization. So critical sections, for example, threads can have maybe waiting there if multiple threads try to enter a critical section at the same time or to more or less the same time. So in this example, the green stripy bit is supposed to represent a critical section which only one thread at a time can execute. If they all happen to arrive at that at the same time, then they have to take turns. Only one thread at a time can be in the critical section. So there's going to be sometimes threads are going to spend some time waiting. What can you do? You can try and think, well, can I minimize the time? Can I optimize the code that's inside the critical section to minimize the amount of time that's in there? OpenMP critical regions are a global lock. You can have critical directives with different names. So if you have more than one separate data structure that you're trying to protect with critical sections, you can use different names. And also, if you can use atomics, then you should, because they are less expensive than locks or critical sections, and they also allow more optimization. Okay? So, for example, if we're trying to protect updates to different array elements, which could potentially happen from different threads at the same time, then atomics are good because they permit concurrent updates to different array elements. You're not actually guaranteed that by the OpenMP specification, but implementations will generally do that correctly or reasonably well. Or potentially you might, if you've got lots of different pieces of data you want to protect too, then you might say, okay, I'm going to use multiple locks rather than the single global lock that critical regions use. Okay, so that's sequential code and idle threads. Next one is synchronization. Okay, so as we've already talked about, every time we synchronize threads, there's some overhead, even if the net threads are never idle. Okay, so just the act of, even if all the threads are at the barrier at the same time, then actually getting through the barrier costs something, and it's not cheap. Okay, so we've already talked about this kind of the overhead. So in terms of clock cycles, it's thousands to tens of thousands of CPU clock cycles to execute a barrier. And similarly, so overhead of criticals and atomics and locks, there's some overhead there. It's not as much as barriers, but they're not free either. And also things like creating a task and executing a task also require some internal synchronization to make that happen. So what can we do? Well, we can think about parallelizing at the outermost level possible to try and minimize the frequency of barriers. And so try and make the pieces of work which are executed by threads inside parallel regions as large as possible, so that we don't execute lots of barriers. That may not be easy. Okay, you might need to reorder loops and reorder array indices to make that happen. If we've already looked at, it's possible to suppress barriers with no wait clauses, but you need to be really careful because there's always the possibility of introducing race conditions by removing barriers that are actually required for correctness. And as I say, atomics may have less overhead than critical locks. In most modern implementations of OpenMP, that's definitely true. Obviously, atomics are restricted. It's single updates to basic types. But if you have that sort of pattern, you should definitely use atomics rather than criticals. Next one is scheduling. Okay, so whenever we, there are opportunities in features in OpenMP that allow us to specify computational tasks and then rely on the runtime to assign these to threads. And then if we do that, we're going to incur some overhead in the runtime for doing that. Some of that might actually be internal synchronization. Okay, so there's a slight overlap between synchronization and scheduling, really, if you dig down into it very carefully. But there's also, it's not just synchronization going on. There's other code is being executed by the runtime to schedule tasks. So examples of this would be non-static loop schedules, so like dynamic or guided loop schedules, and also tasks. Okay, so those are cases where we're relying on the runtime to do some dynamic scheduling of computational tasks to threads. So doing something like this, if I have a very big loop, and suppose that each iteration of the loop doesn't really do very much, then using a schedule which is dynamic with a chunk size of 1 might not be a very good choice, because there's going to be some overhead associated with the scheduling of every single individual iteration to threads. And as we talked about the other day, you need to try and get the granularity of the tasks right. Okay, if your tasks are too big, then you may end up with idle threads overheads because it's not possible to get good load balance. If the tasks are too small, then you might result in scheduling overheads. So there's it's usually a case of trying to find a sweet spot or a range of task granularity that gives you both load balance but also doesn't incur excessive scheduling overheads. So those are relatively straightforward things to think about. The next possible source of overhead is communication, and this is where it gets a little bit trickier. The reason why this is hard is that on shared memory systems, communication is between threads is kind of disguised. It shows up as increased memory access costs. Okay, so we'll see that what's happened is that loads and stores will take longer in a parallel context than they would in the equivalent sequential code. And that happens because it takes longer to access data that's either in main memory or maybe in another processor's cache than it does to get it from the local cache. And you have to remember that on modern hardware, main memory accesses are expensive things. So it's order of 100 or 200 clock cycles for a main memory access, compared with a handful of cycles to do a floating point operation. And communication between processors or cores takes place via the cache coherency mechanism, which we'll talk a little bit more about in a minute. But this is very different from message passing. Okay, so if you are familiar with writing MPI code, then it's very easy to if you show me an MPI code, I can very easily say exactly where the communication is taking place. The communication can only take place inside calls to the MPI library. But in shared memory programs, in multi-threaded programs, this communication is much finer grained. You can't see it directly from looking at the source code. You can't look at the code and say which of those memory accesses are going to take longer because of the behavior of the memory system. And they're also typically spread throughout a program, which is in a way that you can't easily identify. So it makes it much harder to analyze. It also makes it much harder for tools to monitor it as well. Okay, so you can get profiling tools to instrument message passing programs and tell you a lot about how much time was spent in MPI calls and how much data was transferred and all that kind of good stuff. It's much harder to get tools to monitor communication in shared memory programs because the granularity is so fine-grained. It's down at the level of individual memory accesses, and trying to instrument that typically incurs massive overheads in the program and skews everything anyway. So it's hard to get tools to tell you useful stuff about communication. So cache coherency. Okay, so this is the so just a brief bit of background in case anybody's not really too familiar with the hardware. So in shared memory systems with multiple cores, typically every core will have its own level 1 and level 2 caches, and then the level 3 cache is typically shared between either all the cores or some subset of the cores, depending on the processor design. So this fact that we've got lots and lots of different caches means that in order to preserve the illusion of shared memory, then it should not be possible for different caches to contain different valid values of the same memory location at the same time. So the hardware uses this cache coherency mechanism to make sure that that can never happen, so that so that different cores cannot observe different values at the same address. So as a very simplified, the real hardware is very complicated. But a very simplified description, which allows us to think about it in a reasonable way and reason about it, is basically like this. So whenever a thread writes a data item, it will get an exclusive copy of that data in its local cache. Okay, so it will become the owner of the most up-to-date version of that variable. And in order to keep everything coherent, when that write happens, any copies of that data item that happen to be also in other caches will get marked as invalid, so that other cores, other threads running on other cores cannot read out-of-date values. And then subsequent accesses to that data item by other threads must then get that data from wherever the exclusive copy is. And say the details vary. It's possible in some circumstances that the up-to-date copy might be in main memory rather than in the remote data cache, but the cost of that is much the same anyway. But all this takes time because it all requires moving of data between from one cache to another, or between caches and main memory, or between caches, or at least between caches and the last level cache, the shared cache. Okay, so that's a very simplified description of what's going on. So the reality is much more complicated, but at least that gives us a reasonable picture to reason about the behavior of programs. Okay. So what does that mean for performance? It really means that because of the way caches work, data is going to be cached on the processors or on the cores which are accessing it. So we have to try and reuse that as much as possible. So we need to write code with good data affinity. What does that mean? You need to try and ensure that the same thread accesses the same subset of program data as much as possible. Okay? And for reasons we'll come on to, that those subsets have to be should be reasonably large contiguous chunks of data as well. Okay, so threads accessing finely grained interleaved data is also bad. So we'll come on to why that is in a minute. And it's also important, as you know, as a sort of as an aside here, this is also why it's important to prevent threads from migrating between cores while the code is running, which we already talked about. Because if that happens, then all the data that thread has been recently accessing is now in a different cache. Okay, so the thread has moved from one core to another. And then it has to wait, you know, any subsequent accesses by that thread to data that it had local cache, then data has to move. Okay, so Chen is asking, do you have a way to control affinity? So yes and no. Okay, there is, you know, it's down to how you write the program. You know, it's down to make sure that, you know, that the you know, we have programmers have to take care of which thread is doing what, okay, and therefore which thread is accessing what data. Okay. I'll talk a bit more about affinity in the context of main memory in a minute, okay, which is another issue. But really, here I'm largely talking about caching rather than locations in main memory and NUMA systems. So effectively, you know, as a programmer, you have absolutely zero control of what the caches do. The caches do their stuff. They, you know, they implement their simplistic, very high performance hardware, you know, sort of fully hardware implemented algorithms to do whatever they do, to move data around the memory system. And there's pretty much nothing we can do as programmers to affect any of that, okay, except how we write our program. Okay, there's nothing you can do to change what the hardware does. Okay, so here's an example of where things can, you know, sort of thing that can go wrong, or, you know, why, you know, where you could write a program which doesn't have good data affinity. Okay. So I've got two loops here, and the important thing to notice is that these two loop nests are accessing this two-dimensional array A. So the first loop nest writes some values into it, and the second one reads values in A. And look at the second one first, then this is a triangular loop nest, okay, because the bounds for J are 0 and I. Okay, and I is the outer iterator. So if we parallelize the I loop here, then that's not going to be well load balanced, because the amount of computation depends on the value of I. So we might decide to choose a loop schedule for this, which isn't the default static schedule, in order to get some load balance. You know, so suppose we do some experiments. We say, okay, maybe, you know, static with a chunk size of 16, say, turns out to be a good choice. But then we go back to this loop, which is where the array was written. This doesn't have the same pattern. So the loop bounds here are 0 and n. So this is writing the whole array, whereas this is just accessing one of the triangular halves of it. And because this I loop is well balanced, every I iteration has the same amount of work, then, you know, there's no reason to use anything other, you know, a priori. There's no reason for load balance, at least, to use anything other than static here. However, we're now in the situation where, for pretty much every element of A, the thread which writes AI, because of the different loop schedules, the thread which writes AIJ here is a different thread from the one that reads it here. So, you know, we are likely to get a lot of cache misses when we come to do this access here, because the data affinity is not good. So in this example, okay, this would be easy to fix. We could just match the schedules here. Okay, yeah, solution here would be to to use static 16 for the first schedule as well. So another example, so you might find that, okay, so have a parallel loop that reads the elements of AI, and maybe does some more expensive computation here that makes it worth parallelizing. And then we have a sequential loop that resets the values of A to something, and then we repeat the parallel loop that reads A again. So what will happen, if you think about the cache coherency mechanism here, what's going to happen is that bits of A are going to get distributed across different caches where the different threads executing this loop are running. And then the sequential loop, so provided that provided A fits into, say, level 2 cache, then this will get exclusive copy. This write will get all the exclusive copies of all of A, all the elements of A in one cache, and invalidate all the other copies. And then all these accesses subsequently have to go to that one cache to get the up-to-date values. So if you did some careful measurements here, you might observe something interesting. So what you would see is that the execution time for this sequential loop would actually increase if you go parallel in these loops, okay? Because the invalidation mechanism takes some time to happen. So you can have this kind of non-intuitive behavior where parallelism elsewhere in the code can actually affect the performance of sequential bits of code because of the communication and data movement that's going on. So in this case, well, solutions, we could parallelize this loop. We might also be able to say merge these. Might be possible to say merge these two loops together. That would be good for sequential performance as well. But that depends. That might not be trivial. Okay, these could be in different. In principle, these could be in different functions somewhere, and merging them together might be a big refactoring job. Okay. Yeah, I think I've said all that. Okay, it gets worse. Okay, so and this is NUMA effects. Okay, so far we've really been thinking about data affinity with respect to caches, but on multi-socket systems or modern processors like the AMD ROMs, which are in ARCHER2, we have multiple memory domains per chip there. Okay, and when that happens, then the location of data in main memory becomes important as well, because main memory is actually physically split up into different bits, which are more closely attached to some cores than others. All the memory is accessible from all the cores, but the speed of access is different. So pretty much for reasons, okay, pretty much all supercomputers these days are multi-socket. Most systems have two chips per socket. Okay, so you're 2 chips per node, as I say. And then we're also seeing with large core counts, we're also seeing multiple NUMA domains per chip as well. So the AMD ROMs on ARCHER2, every node on ARCHER2 has 2 chips. Each chip has 64 cores, but the memory attached to each chip is split up into 4 NUMA domains. So every 16 cores are attached to a separate piece of main memory, effectively. Okay. So OpenMP doesn't have any real support for controlling this. Okay, so you can't directly control where your data is placed in main memory. That's down to the operating system to decide. And common default policy, so particularly for Linux, is so-called first touch policy. So it will place the data on the processor or in the NUMA domain where the first access to that data comes from. So for single-threaded processes, that makes total sense. For MPI programs, where every process is only accessing its own data, more or less, that also makes total sense. For OpenMP programs, this can be the worst possible thing to do. Okay, because what happens is, it's entirely possible that all your data initialization happens in the master thread. It's not parallelized. And then all your data gets allocated into one NUMA domain, and having all threads access the data in the same socket becomes a major bottleneck. You basically, it's mostly the memory bandwidth issue that happens here. Okay, so memory bandwidth is at a premium in most and is the limiting factor for a lot of applications. And by having all your data in one NUMA domain means that you are basically restricting your memory bandwidth to the bandwidth available for that bit of main memory, and you're throwing away. If you did decide to run, did want to run an OpenMP program on all 128 cores on a node, then you can end up having access to only 1/8 of the available memory bandwidth if you're not careful. Okay, what can you do about it? There's some systems there is a command called NUMA-CTL, which will change the policy from first touch to something else. So typically round robin, so it'll just spread the pages of data around the memory system. A bit of a crude tool. Will help. Will be better than nothing, but it's a bit crude. Really what you have to do is, if you're in this situation, is to control your data placement indirectly by parallelizing your data initialization. So that might seem completely not worthwhile in terms of the time it takes. You might run your application code might run for hours, and the data initialization is all done in the first 3 seconds. But those first 3 seconds is going to affect the performance of what happens in those first 3 seconds is going to affect the performance for the rest of the runtime. So you don't necessarily have to get the distribution exactly right, and there may not be an obvious exactly right distribution for your data. But the point is, is really to have at least getting some distribution, so that you really are using all the available memory blocks in the system, and not throwing away memory bandwidth. And when you're doing this, just remember that the allocation's been done on an OS page level. Okay, so those are typically order of kilobytes, and it's maybe careful if you did decide to use large pages using megabyte-sized pages, then that makes distributing your data a little bit more tricky. In practice, if we're thinking about hybrid MPI plus OpenMP programs, all of this generally means that it's never a good idea to run OpenMP programs outside of a single NUMA domain. Okay, so for a system like ARCHER2, it's almost never beneficial to run more than 16 threads per MPI process because of this problem. Okay, and it gets worse. Well, sort of gets worse. Okay, modern processors, their cache coherency mechanisms contain some tricks for mitigating false sharing. So it's not actually quite as bad as it used to be in some older processor designs. But the problem here is that, talked about these cache coherency operations, so invalidating words and making exclusive copies and moving data around between caches. The units of data on which that's happening is cache lines or cache blocks. So, and the size of those is typically 64 or 128 bytes, something like that, okay? But almost always bigger than a single word, okay? So our data words in our programs are typically 4 or 8 bytes, depending on whether they're integers or double precision floating points or whatever. Okay. So that means that even if different threads are not actually sharing any data values, but if we have the situation where different threads are writing to neighboring words in memory, and if words are neighboring in memory, then they are going to be stored in the same cache block. That may cause cache invalidations to happen. Okay, and that's still a problem even if we just have one thread writing and the others reading. If all threads are reading, it's not a problem. Okay? Every thread just gets a copy in its own cache. Nothing ever. The values are not. If the values are not changing, nothing gets invalidated. Okay. So the worst kind of problems occur. Worst kind of patterns occur where you have different threads repeatedly writing neighboring array elements. So, for example, if you had if I wanted a shared array, and I'm going to use that to count something on every thread. So I would index, have a shared array that's indexed by my thread number, and maybe and incremented frequently. Then that would cause exactly that sort of problem. But it can happen in other cases as well. Again, if I have one of these triangular loop nests, and in this case, the parallel loop is writing into elements of neighboring elements of an array. So the parallel loop index is used to access a one-dimensional array here. Then using a static schedule with a chunk size of 1 would also cause this problem potentially. Okay. Well, in this case, you might get away with it. The compiler might manage to optimize these, might manage to do some user register to accumulate values, but in general, this can still be a problem. And in this case, what you would find is that a chunk size of 1 is not a good choice. Okay, you would need to have a larger chunk size to make sure that the blocks of data that each thread are accessing they're basically bigger than a cache line, bigger than a cache block. Okay, so communication is is quite difficult to. There's lots going on there. I say it's all down to memory accesses and working out what actually happens when you run a program in terms of the memory accesses and all the cache behavior that's going on, etc., is actually quite difficult. The last main source of overhead is hardware resource contention. Okay. Because why is that? Okay, well, just because the design of shared memory processors is such that there are performance trade-offs here. There are shared resources which don't scale if all the cores try to access them at the same time. On the other hand, you can think of it the other way around. You can think of it, well, it's good because if I just run an application on a single core, then that gets access to more than its fair share of resources. which is fine, but it just means that you're, if you look at scaling inside, across multiple cores, then hardware resource contention can be a cause of poor scaling. You can think about it as well. The one-threaded version is getting artificially boosted, but nevertheless, the effect is the same. So in particular, things we might care about, so cores and therefore the OpenMP threads which are running on them contend for, as I say, we've already talked about memory bandwidth, it's a big one. Okay, cache capacity, if we have shared caches, and also functional units, so things like floating point units, if we use simultaneous multi-threading. Okay, so if we actually run more than use the hardware threading, hyper-threading, whatever you like to call it, to virtual cores, has too many different names for the same thing. Okay, if we run multiple OpenMP threads per hardware core, then they will also contend for the floating point units. Okay. Yeah, so memory bandwidth is a big deal. So codes which are very bandwidth hungry or even moderately bandwidth hungry will not scale linearly on most shared memory hardware. Okay. What can you do? Well, you really just have to think about try to reduce your bandwidth demands by improving locality and hence reuse of data in caches. And that's going to benefit the sequential performance as well. So memory bandwidth is such a big deal that on modern processors that there are cases, and I have seen, real cases where it's actually worth trading off extra computation for against memory accesses to reduce the memory bandwidth demands. So it's worth computing things, it's worth recomputing values. Turns out to be cheaper than storing them in main memory and reloading them again, because it avoids, you've got lots of floating point capability and you have limited memory bandwidth. Okay, so I've a little bit of an example to go through. I realize I'm getting a bit short of time here, so I'm going to go through this reasonably quickly. But this is just an example to show how bad this problem is really. Okay, so this experiment was done on one of the was done on ARCHER2, so an AMD Rome processor. And I'm only looking at one NUMA region, so only going up to 16 cores, and I'm making sure all my threads are running in the same NUMA region. So there's no NUMA effects going on here at all. Okay, but it means that all the threads are contending for the same memory bandwidth in that NUMA region. So this chip, we've got level 1 and level 2 caches per core. And then there's a slightly complicated design. We have 16 megabytes of shared level 3 cache for every set of 4 cores. Okay. So what I do is just run this very simple parallel loop. The fact that it has a reduction here is not relevant. The only relevant thing for performance here, and the floating point is not relevant either. Basically, the entire performance is really down to the cost of accessing this array. Okay. So what I'm going to do is vary the value of n and therefore the length of the size of the array that's being accessed and the number of threads, and measure how much speed up I get. So this is what we end up with here. So this is a plot of speed up, okay, the speed up I get versus the value of n, so the number of loop iterations on the x-axis. So I have a different curve depending on how many threads. So this is speed up for different numbers of threads compared to running one thread. So what can you see? Well, if you look at the bottom left-hand corner here, so for small numbers of loop iterations, the speed up is actually much less than 1. Okay, and this is just the result of the overhead of the parallel region. Okay, this code is very efficient. It vectorizes nicely, and so it runs really well. But it means that I really need quite a lot of iterations in order to overcome the overhead of the parallel region. So in fact, for large numbers of threads, I need at least 100,000 loop iterations just to get a speed up of 1. But you can see for 2 threads, okay, once the loop's big enough, then I end up with a speed up of 2. Okay, great. That's kind of what I'd hope for and expect. I go to 4 threads, so that's the orange curve here. I do briefly achieve a speed up of 4, but then it drops a bit. And in this region here, the data fits in the level 3 cache, but not in level 2. Okay, so at this point, the different threads, so I'm running 4 threads, they're all attached to the same level 3 cache. And so this is contending for the bandwidth from the level 3 cache. So I don't quite get, I get like 3.5 times speed up and not 4. But then as the size of the loop and the size of the data gets even bigger, then it no longer fits in level 3 cache anymore. And all the accesses are coming from main memory, and the speed up drops back down to about 2. So for large enough arrays where all the accesses are coming from main memory, then it's really hard to get anything bigger, even if I go up to, so this is 2, 4, 8, 16 threads. Basically, I've completely saturated the memory bandwidth with just 2 threads. For 8 and 16 threads, okay, you get this weird effect because 8 and 16 threads now have access to more level 3 cache. So for this sort of range of this a narrow range of values here, where the data doesn't fit in one level 3 cache, but it does fit in maybe in either 2 or 4 level 3 caches. So you get this sort of superlinear speed up effect. So it's actually possible at one point to get 16 times speed up on 8 threads, but that's purely because I have access to double the level 3 cache capacity. But yeah, so the real message here is that if I'm running in levels, in shared level caches and particularly in main memory, then the scalability is really poor because of contention for bandwidth. Okay. Can also contend for cache space. Okay, so if we've got multiple cores running and on cores which are attached to the same level 3 cache, then if you're running a single thread, then that gets access to the whole cache. If I'm running, as in case of ARCHER2, in case of the AMD Rome, if I'm running 4 threads on the 4 cores attached to the level 3 cache, then they basically each get a quarter of the level 3 cache capacity. And then also, as mentioned before, if we're using hardware threads, OpenMP threads running on the same core, they contend for the functional units as well as the cache space and the memory bandwidth. So actually, utilizing hardware threads is rarely very beneficial for a lot of scientific applications, and that's why you'll find on systems like ARCHER2 it's disabled by default. Okay. If you want to run more than 1 thread per hardware core, then you can, but you have to do something special in your bash script to enable that, because generally speaking, it's not beneficial. Of course, the other way of getting hardware resource contention is by oversubscribing. Okay, so running more threads than you have hardware execution units is generally a bad idea, because then the operating system has to give each thread a fair share of the execution units, and the cost of stopping one thread and starting another, doing a context switch, is high. It's thousands of clock cycles, and as we've already talked about, it's going to cause, it's the same problem as if threads are migrating. Threads, if we stop one thread and start another, then we're basically ruining our data locality and data affinity. Okay, so those are the main 6 causes of poor performance. The other possible one, which you might be unlucky enough to come across very occasionally, is compiler non-optimization. So in rare cases, adding OpenMP directives can actually inhibit the compiler from performing its sequential optimizations. And the symptoms you'll get there is that the one-thread parallel code has a longer execution time than the sequential code compiled without OpenMP. So adding OpenMP does something, has some bad interaction with the compiler optimization. If that happens, it's nasty. It can be really hard to find a workaround. There are some things you can try. Making private copies of data or local copies of variables can sometimes help because the compiler can do better analysis on them. But in generally speaking, it's a nasty problem. But say, thankfully, happens very, very infrequently. Okay, so realize I'm pretty much out of time, but just to sum up, think a little bit about the process of performance optimization. Okay, what do? My code's giving poor speed up. I don't really know why. What can I do about it? Okay, so I hope I convince you to say, okay, no, this is not, this is OpenMP is not terrible. It's don't give up. I think what you can think about doing is if you can classify and localize the sources of overhead. So what I mean is you can work out which of those 6 issues is a problem. Okay, maybe it's more than one of them, and whereabouts in the code it's happening. Then you have a good chance of being able to fix it and do something sensible to improve the performance. So use tools by all means. Timers, hardware counters, maybe profiling tools can be helpful. And obviously, if you can quantify the overheads, then that's also helpful because you really want to fix the problems which are responsible for the big overheads first. And then once you fix one problem, measure again, iterate until either the performance is good or you can't figure out any better fixes, or at least you understand what's causing the problems, and you can reason that that's something that you can't easily fix. And profilers, so the sort of standard profilers that you get in things like gprof that comes with Linux or IDE profilers can be pretty confusing in a multi-threaded context, because typically what they will do is they show you the accumulated time spent in functions across all the threads. So you can't really it's difficult to get much sense of load imbalance. If different threads are taking different amounts of time in a function, it doesn't really show up very clearly. I find using timers very beneficial. If you add timers around every parallel region and also around the whole code, or at least the whole part of the code that you're interested in the performance of, then that gives you a really good handle on working out which parallel regions have the worst speed. Which ones, where's the time going? Which parallel regions are costing? Which ones have the worst speed up? Because it means you can do runs on different numbers of threads and easily do the comparisons, which is actually rather hard to do with profiling tools. So looking at doing profiles with different numbers of threads and comparing profiles is not that easy. So that's I do find that a good tactic. There are a bunch of performance tools out there, so it may depend on what you have access to in terms of what systems you're running on. Some of these things are free, some of them are not. So I'll just highlight a couple of them here. Scholastica is an interesting one. It's a free tool. It can be quite difficult to get it to build with large applications, but when it does work, it's very nice because it does do this. It does sort of take this approach of has this view of breaking down overheads into different categories, apportioning execution time into compute, useful compute and different types of overhead. Most of these tools, though, are not very good at diagnosing memory issues. Okay, so communication issues, cache misses, memory bandwidth contention. Most tools really don't do a very good job at that. But one that does is this one called Thread Spotter, because again, this works differently. It basically takes a statistical trace of the memory accesses and then replays that through cache simulators. So that's much better at detecting. It can tell you much more about what's going on in the memory system, including things like false sharing, which other profiling tools can't really do. Okay, yeah, there's a practical exercise associated with this, which you're welcome to try out. But otherwise, that's it. Does anyone have any questions? So the best is always the best is not always. The best is 16 or fewer threads, and typically actually fewer. Okay, but but because there are 16 cores per NUMA region, running more than 16 threads per MPI process is almost never going to be a good solution because of the NUMA effects. There are rare cases where it might happen, but almost if you for most applications, it's 2, 4, or 8 threads per MPI process is usually. But we'll talk about hybrids, OpenMP and MPI in a lot more detail in the next session. Thanks, Marco. Very welcome.